Today we're going to look at deep reinforcement learning, but before we get to that, after the break, we're going to cover the basics of reinforcement learning. So this first part will be an introduction to the fundamental ideas and concepts that then we're going to adapt for deep reinforcement learning problems. I'm going to start by giving an introduction to what reinforcement learning is and how it differs from supervised learning and unsupervised learning that we've been seeing so far, and then talk a bit about Markov decision processes and the policies, plans, and so on. So these basic concepts that we're going to need to understand the adaptations we'll make for deep reinforcement learning. And then we'll look at algorithms for improving policies when we have the Markov decision process. Then we're going to need to adapt those for more realistic problems, but this first lecture will be about just the fundamental ideas. So let's start with reinforcement learning. When we are doing supervised learning in deep learning, we have some target value that we want our model to output. And so we're going to fit the model in order to minimize the error to this target value. So we present a model with examples, with labeled examples, and we adjust the parameters of the model so that we, at the end of the process, get a network that is approximating the target. So we are using supervised learning in that case because we can supervise the learning process by measuring the error for each example. Unsupervised learning with deep neural networks is very similar to supervised learning. From our perspective, it seems different because we are not using labels, but from the perspective of the network is the same thing. The only difference is, for example, with autoencoders, we want the target to be the same as the input, and so we don't need additional labels. But for the network, we are minimizing this error and measuring the error on each example. With reinforcement learning, we have a different kind of problem. We have an agent, which is something that makes decisions. I put a picture of a robot here, but if we had really a robot, the agent would actually just be the software controlling the robot. And everything on the hardware, the wires and the arms and the motors and things like that would be part of the environment, because that would be what the agent would be deciding to affect, to interact with. So the agent basically chooses what actions to make, and everything else that then is affected by those actions would be the environment. And we can consider that depending on the actions, the environment will change its state. And now the agent receives information about the state, which comes in basically two different types that we're going to separate when we are considering the reinforcement learning problem. One is the observation. The observation may be exactly the state if we are dealing with some abstract problems like playing checkers or chess or things like that, where we can really encode everything about the state. But when we are using more realistic problems like driving a car, the observation is just something that we are getting, some kind of information we are getting about the state, but it may not be giving us the complete state of the environment. So I called here the interpreter whatever system is giving us observations about the state. It can be a set of cameras, sensors, something like that. And it also occasionally gives us this reward. The reward is an indication of how good things went when the agent took the action. So basically the agent decides which actions to take. This will have an impact on the environment, and then the agent gets some feedback by observing what changed in the environment, and also sometimes getting an indication of whether things went bad or well. So this is a different problem from supervised learning and unsupervised learning, the kinds of problems that we've been seeing so far. Because we are not getting, let's say, a data set with all the examples that we need and the target values, we have this cycle where the agent has this information about the state of the environment, what the state is and how good that state is, then it will have to adapt its decision algorithm based on the experiences it had so far. It will choose an action and then receive further input depending on the action chosen. So basically, the agent is gathering data while it's learning instead of just having a large batch of data from the start. Okay, so let's see this in a bit more formally, this kind of process that we have here. And we're going to represent this as a Markov decision process. This is a useful abstraction for computational purposes and for the properties that these chains of actions and observations have, is to assume that we have this Markov property. The Markov property in a stochastic system that is taking place over time is the property of having no memory beyond the last state. This can happen in games like, for example, chess or something like that, where what matters are the positions of the pieces on the board at this moment, independently of the trajectories of how they got there, because that will not make any difference. If we know where the pieces are right now, it doesn't matter what kind of moves we did before. It will make no change for the decisions we have to take. Of course, this may depend on how we represent the process. So imagine that you have a bag with blue and white marbles. At some point, you've been taking marbles out of the bag. At some point, the probability of getting a white marble will depend on all the marbles that came out before, because if many blue marbles came out before, it's more likely now that we're going to get a white one, because we have fewer blue marbles in the bag, and vice versa. So if we are just looking at each marble or remembering each marble that comes out of the bag, we need to remember everything before, and this will not have this Markov property. But if we observe the contents of the bag, that is, we describe the state at each instant to be the number of white and blue marbles in the bag, then it's irrelevant what happened before, because the probability of drawing a white marble at this moment depends only on the number of white and blue marbles in the bag. So we are going to, in reinforcement learning problems, represent the state in a way that preserves this Markov property as best as possible, because without this we would have to keep track of all the trajectories that took us to each particular state, and basically the kind of approach that we have here would not work. So this is an important assumption, and when you're trying to solve a reinforcement learning problem, remember that the information your agent needs to do the decisions at each state should encode everything necessary so that we preserve this Markov property, and the agent doesn't have to remember everything it did in the past. So we can just include all the relevant information in the state. Like, for example, in this case of the bag, we would just describe the state of the bag to the agent so that the agent could decide something. Okay, so we can define a Markov decision process as a tuple of these elements. The set of states that the environment can be in. For example, if we are playing checkers or something like this would be the complete set of possible positions and combinations of pieces on the board. A is the set of actions the agent can take, so we need to fix what are the possible actions. And we have then these probabilities of transition from state S to a new state, S prime, given some action. So if the agent chooses action A at state S, there is some probability that it will fall then on this state S prime. And we would need this table for all the different transitions. So the probability of being at state S prime at time t minus 1, t plus 1, given that when the agent was at state S, the agent chose action A. This may be a simple mapping if the system is deterministic. So if choosing action A at state S will always result in S in some particular state, then we would just need to have those mappings. But in theory, the system may be stochastic, so the agent can try to influence the outcome, but the outcome may be different even if the agent chooses the same action. So this would be a more general table of probabilities of transitioning between states. Then we need the reward. The reward is what informs the agent of how well things are going. So basically what we're trying to do with reinforcement learning problem is to maximize the return we get over a set of actions. So when a reward appears, this is an information that we are going on the right track. And we can, in general, specify the rewards to be some amount that we receive when in state S we choose action A and then we fall into state S prime. So for all these combinations, there could be a reward. In practice, usually the reward is just associated with the state. So you reach some point and at some particular state you get a reward regardless of whether of what action you would take. So we would associate the reward in this case with S prime, which is the destination state, and it would be the same regardless of what the state was before and the action. But in a more general approach, we could make the reward depending on the action chosen and the previous state and so forth. Now we need an initial distribution of states. So this is the starting point for the problem. There is a probability of being in some particular states. And then we need also to specify this discount factor. This is an important parameter because this is how much we are going to discount future rewards. If we get reward R at time 0, then if we were to delay this reward and get it at time t, it will only be counted as gamma raised to t. So if gamma is generally smaller than 1, that's what makes sense here. And so as we raise gamma to some power, we get increasingly shrinking numbers. And basically what this is telling the agent is that it's better to have the reward earlier rather than to let time go by and get the reward later. So by controlling gamma, you can determine how urgently the agent is trying to get the reward. If you have a small gamma, then the agent will try to get the reward sooner because the discount is steeper. If you have a large gamma close to 1, then the agent will not be as much concerned with getting the reward sooner. And then we need the planning horizon. This can be infinite if we have a game that never ends, or it can have a specific number of turns that will terminate, so we can know in advance that we don't need to plan for more than those steps. Okay, so let's look at a specific example to understand this better. We have this frozen lake. This is a classical example. The agent always starts here, so this distribution of initial states is just this starting point. This is a frozen lake. There is snow around here. You cannot leave the board. And all these frozen cells with F are safe to walk on. So we can move around the frozen surface of the lake here. These are holes. They are terminal states because if the agent falls into a hole, it cannot no longer leave and the process terminates. And this is the goal, which is also a terminal state. We want the agent to reach there, and that would be the purpose of walking around the ice. So we need to determine these probabilities of going from each state to another with some given some action. And since the ice is slippery, what we're going to do is when the agent decides to move in a direction, for example, if the agent is here and tries to go south, there is a 1/3 probability that the agent will manage to go south, but 1/3 probability that it will slip to the right or to the left. So it can go west or east with equal probabilities. And this would be basically the table that we could use for those probabilities. If we are at state 0 and the agent decides to go north, then there is 1/3 probability of actually trying to go north. And since there is snow there, it will not exit the location. So the state will still be 0 again. If it tries to go north, there is also 1/3 probability that it will go east, and so it will go to state 1. And there is 1/3 probability that it will try to go west, but since there is snow there, it will not leave. So if we are here and try to go north, 1/3 of the time will go into this state, and 2/3 it will not change. So the same thing if we go south, and then if we are at state 1 and try to go north, and so on. So these tell us, this table would give us the probability of transitioning from one state to the other, given the state where we are starting and the action the agent is choosing. Now we need the reward. The reward will be 1 when the agent reaches a goal and 0 everywhere else. So here you can see one kind of problem in reinforcement learning, which is that the reward may occur in seldom situations. So may occur seldomly, and we don't have information for every action that we are taking. The starting point is here, S. The planning horizon, we can consider 15 steps, for example, or we could consider more. So basically 15 steps could be, if we don't reach the end in 15 steps, then the game is over and we don't need to plan for more. That would be one possible rule. Or we could have a larger planning horizon if we take into account that the agent may slip and then fall back and may go around here in turns for more than that number of steps. Now we need to choose a discount factor. This is this parameter that will favor the bringing the rewards sooner. So suppose that we have t, this uppercase T time steps that we are taking, and we are trying to evaluate what is the expected return when we are at this small t here. So suppose that we are at time 1, for example, and we want to evaluate what would be the return in the future, how we are going to evaluate it at this moment. We would add the reward for the immediate step that we're taking. So we're going from the current state to a new state at time t plus 1, and the reward for that we get in full. But then we can estimate what reward we're going to get after this, in the second step. That one will be discounted by gamma. And in the third step will be discounted by gamma squared, and so on. So the return we are counting, we are evaluating at time t, is the sum of all future rewards, but with increasingly distant rewards discounted by an increasing power of gamma. Note that this return evaluation will depend on the time. So basically, if we are here at state 0 and need to do several steps until we reach the goal, the reward of 1 for the goal will count for the return at state 0 with a large discount for all of these steps. But if we are here, then the reward for the goal will count for our return at this point in full, because it's just one step away from what we have. So this discount value makes the agent look for closer rewards sooner rather than later, and the smaller the discount value that we have, the gamma parameter, the more the agent will give importance to sooner getting the reward sooner. Okay, so now let's look at how we can plan our trajectories here and the difference between a plan and a policy. We could make a plan to go from the starting point to the goal by doing these steps. So we could go east, east, then south, 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 and then east again. The problem is that since the ice is slippery, when we try to go east here, we could slip and fall into this location. And the same thing when we try here, we could fall here. And so there are lots of places where things could go wrong, and then we would be outside our plan. So a simple plan is not sufficient in general when we have some uncertainty about the outcome of our actions, for example. And what we actually need is a policy. A policy is a specification of the probability of each action at each state. And this allows us to obtain the plan, so to speak, starting from any state. Starting from this one, we would go east and then south and then east again. But if we fall outside, for example here, then our policy is telling us to try to go back west to go into this path here, or if we fall to this location, we try to go this way, and so on. So this is basically what we're going to try to find, which are policies, and these are you can think of them as a large table that is telling us for each state what is the probability of taking each action. The policy can be deterministic, so it just says that, for example, at state 0 we always go east, or it could be stochastic. You could have a probability distribution and try to go different ways with the different rolls of the dice. For this, in this part, we're going to assume that the policy is deterministic, which is easier to manipulate and to understand. But for a more general approach, remember that the policy can be probabilistic and give you probabilities of different actions at each state. So here are two different policies. One is greedy because it tries to go quickly towards the goal, for example, going this way. If the agent sleeps, it can go this way, and so on. But this seems a bit risky because, for example, in this step, we have a 30% chance of falling in this hole. When we reach this step, we have a 66% chance of falling in one of these holes because only 1/3 of the time will we go south and the other 2/3 will go either east or west. So this one is probably a bit risky because if we fall into a hole, we get stuck and we will not be able to finish and get the reward. So this could be a safer policy here. First, we try to go on this side, so we may drop here, but we have when we reach here, we keep trying to go this side so that we don't have any probability of falling into this hole. In this part, we try to go north so that we don't fall into the hole, and so on. So this would be a safer policy that uses the fact that the ice is slippery to guide us in the safe path, avoiding the holes. Now, the question is, which one of these is better? How can we compare them and figure out which one is better? So we can consider the state value function. State value function gives us the expected return. So the return is the discounted sum of all the future rewards. And this gives us the expected return from each particular state. So for state S, the state value function, assuming policy pi, remember that the expected return from this state, for example, will depend on what policy we're following. If we follow this greedy policy, we'll get a different expected return than if we follow this safer policy. So the expected return at S following policy pi will be this average value of the return, the discounted return at state S. This is simply what we mean by the state value function. But this is the expected value of the reward at the next step, plus the discounted reward at the second step, and so on when we start from state S. And we can write this recursively by saying that the state value function at state S is the expected sum of the reward for the next step and then the return discounted by gamma after that step. So the return for the state we attain after this one step, but now discounted by gamma because we are looking at that return from a previous step. So we can write this with the Bellman equation. These are the equations of this form. I'm missing here the principle of optimality. Let me just fix this. Okay, not heavy. But in any case, this principle of the optimality is if you have an optimal policy, then you can just consider the next step here and then keep following the optimal policy from then on. So you can basically decompose this into the first step and everything that comes after. So the first step will be, if we have this policy pi, then we can think of the action that we're going to take, and this will be for each action in this particular state. Our policy is giving us a probability. So we're going to sum over those probabilities multiplied by the sum of what happens after we take the action. So let's say for action A, we have a specific probability for action A in state S, and we're going to multiply that probability of taking action A by all the possible consequences of that. So for all the possible states that we are going to fall into after this action, we're going to use the probability of going from S to S prime using A. Remember that the result of our action may be probabilistic. For example, in the case of the frozen lake, we try to go north, but sometimes we go east or west because we sleep on the ice. So if we try to go north on a particular state, we are going to see what happens if we go east with some probability, west or north, and we're going to add all of these branches, each one weighted by its probability. And what the return we get from those is the reward we get for that particular step, if we change the state towards that step, plus the return that we get from that state onwards all the way to the end, but discounted by gamma. So this is the idea that we are decomposing the step we are taking. So all of these terms are for the decision we are taking now and the reward it's going to give us immediately on the next step, plus what the state value function tells us about the next state we are falling into, but discounted by gamma because this is still in the future. This will be the next state. So this is what we can use to think of the state value function as decomposed into each particular step and everything in the future discounted by gamma. So we can do the same thing for the action value function. The action value function gives us the expected return for choosing action A at state S. So while the state value function tells us about the expected return at state S when we follow this policy, pi, so it's going to consider all the possible actions at state S using this policy. The action value function is giving us the expected return for each particular action. So what is the return from here to the end if at state S we choose action A? We can again write this as decomposing this as the reward for the next step and then the return after that discounted by gamma. And the Bellman equation for this would be, given that we chose action A at state S, we are assuming policy pi, so everything that's in the future, we'll assume that we are following this policy. But choosing action A at state S, we have to figure out where the next state would be. So there is this transition probability of going to S prime, given that we chose A at state S. We have to sum for all the different possible outcomes of using action A at state S, and weight with the probability of each one the future return from that, which is the immediate reward we get from going from S to S prime, plus the discounted state value of the state that we're going to achieve S prime. We can also consider this action advantage function, which is how much better on average we have when choosing a particular action A, with respect to what would be expected under the policy. So remember that the state value function will consider all the possible actions that we're going to take, and will weight the returns according to the probability of each action. But now we can consider the action value function for one particular action and see what advantage that one has with respect to following the policy. So if the policy is giving us an action that is not as good, we will get a positive value here in the action advantage function, indicating that there is an action at this state that is better than what the policy is telling us. So this intuitively gives us an idea of how we can improve the policies. So to optimize the policy, we can replace the action the policy is recommending in a particular state with an action that has an advantage, that gives us a better return in that state. And basically what we want to do here is to find a policy that maximizes the V function and the Q function. So the V function is the state value function, and what we want, we find the optimal policy pi when we obtain the optimal optimal state value function, which is obtained by maximizing the state value function for all possible policies. And the idea is that we find a policy that gives us the optimal value for all the possible states. That is, we get a value that is larger or equal to all the alternatives with different policies. And the same thing for the action value function. We want to find a policy that maximizes the expected return for the actions in all particular states. So converting these with these Bellman equations, we can consider that we obtain the best state value function when we maximize for the actions. So this would be what the policy is telling us. The policy is telling us to choose an action, and if we choose the best action at each state, then we get the best return there. So we're going to maximize for the different states, different actions, sorry, the probability of the next state multiplied by the return. And we find the action that gives us the best future return. Note that this probability is for when the state changes in a stochastic manner, like we are seeing in the frozen lake, because choosing action A doesn't guarantee that we're going to fall into that particular state. So we need to sum over all the possible consequences of choosing action A according to the probabilities of each. But we are trying to maximize relative to the action that we're choosing. And for the action value function, it's slightly different, because with the action value function, we have a value for a state and an action pair. The action is fixed here. So what we want to maximize is, given that we chose the action A at state S, and given that we have probabilities of going to state S prime, what we can maximize is what happens in the future. So maximizing the action value function requires maximizing everything that is going to happen in the future. Here, sorry, this is wrong. This is the state. This should be this term here. So not Q. It should be this term here. So we would be maximizing under that policy everything, the state of the value of the state that we fall into with this action. So this expression here should be no, okay, sorry, it's correct. We want also the maximum action in the future, but basically we can consider that what happens in the future, we can consider it to be the value, the maximum value of the state that we fall into the future. So when we want to do this optimization, we first need to find the state value function for a particular policy. And the question is, if we know the policy, for example, we have this policy here, how do we find what is the expected return for each state? One way of doing this is this iterative policy evaluation, where we start with an arbitrary set of values on our state value function, in state value table, for example. Imagine that this is a table. We just need to set 0 for all the terminal states, because when we reach a terminal state, there will be no future rewards at that point. So we set those to 0, and we initialize the remaining states arbitrarily. We can set everything to 0, for example. And now we're going to apply this policy evaluation equation to convergence. So what we should have in the estimate for state S is the weighted sum for given the probabilities of choosing different actions, and the weighted sum for the probabilities of having different states when we choose action A in state S. So this would be a sum sign here too. Basically what we have here, we are considering the sums for the what happens in the future, depending on the action that we choose and the state that we fall into after that action. And this would be the reward that we get for each particular step, and added to the discounted return for that state. So you can imagine that if we start with this, for example, all at 0, then of course our estimate for what happens next will be wrong, because we are starting with an arbitrary value, but we have some information about the reward. The reward is the information that we're getting from reality, from the system, and it tells us that if we started, for example, at 0 in this in the first iteration, then the reward is telling us that we need to increase this value because there is a reward in this particular state. And so when we apply this evaluation again, this particular state already has some value because it knows there is a reward, and this will propagate to the previous states and so on. So basically, if we do this iteratively, we will propagate all the discounted effects of the rewards over all the states, depending on how we can get there using the policy, so the probability of taking the action, and depending on how the states evolve in that particular system. And so we can propagate the values of the rewards discounted by gamma through all the different states. So there should be a plus sign here between these two. I have to fix these equations. Okay, so let's see this an example with code to explain this better. We can use the frozen lake environment. You can get it in the OpenAI gem if you install the gem in your Python environment. And now you can create the frozen lake environment and get the full MDP. So this is the description of the Markov decision process, where you have for each state, each possible action, what are the probabilities of going to some particular state, what are the rewards, and whether or not we fell into a terminal state, either the whole or the goal state. So this dictionary of dictionaries gives you these tuples that are with probability, in this case 1/3. We will go to state 0 and get a reward of 0 with a probability of 1/3, the other state, and so on. So this allows us to compute all of these terms here. So the probabilities of transitioning from one state to the other, depending on the action that we chose. This is given by these tuples here. So if at state 0 we choose action 0, we have this probability distribution of going to the different states and getting different rewards. We now need a policy. So let's say we have a policy pi. This can be a dictionary that tells us which action to take at each state. So it will tell us this. I'm representing here as a sum over different probabilities, but actually if we consider a deterministic policy, then instead of having this sum, we can take it out and we just choose A with a probability of 1, so we can ignore this part. So this would be how we could do the policy evaluation. We have the dictionary pi that gives us the action for each state. We have this MDP, the full description of the Markov decision process with all the probabilities. This is a discount factor and a tolerance to determine if we are if we converged. So this would be the minimum, the maximum difference between one iteration and the other to decide that we have converged. And now what we do is we start with an empty state value function. Everything is 0. And now we're going to loop through all the states in our Markov decision process. And we're going to, for each state, loop through all the probabilities for the next state for the action that we chose. So basically, if we go back here to the dictionary, for each of these states, we're going to pick one action and then loop through all the different possible outcomes of choosing that action in that state. So this would be this term here, where we are considering the probability of transitions given some action between state S and state S prime. And now we're going to add to our state value function, the new iteration, the probability of going for, in this particular transition for that state, multiplied by the reward we get in that state, plus the discounted return that we expect to have from that state. Now the return we expect to have is in the previous version of our state value function. So vk, and this would be vk plus 1. The one important detail here is that we must make sure that when we reach a terminal state, so done is true, we do not have any expected future return from that state, because we fell into the hole or we finished the game, and so we are not going to receive any more rewards. And in that case, this will be 0, so this term will all be 0 for terminal states. And now we update our state value function and check if the difference between the new one and the old one is sufficiently small. If it is, we just return it, and we finished evaluating the policy. So now we can compare these two, assuming a discount factor of 0.99 for the gamma. You can see that the greedy has a very low expected return from the beginning because it's likely to fall into a lot of holes, and in general it has a low expected return over all the states here. So the safe policy is better than the greedy one. We can compare the numbers, which are the expected discounted return at each particular state given the policy that we're following. So this tells us how we can compare policies. Of course, we could now randomly generate policies and compare them to try to get the best one, but that would not be a very efficient way. What we can do is note that, as I tried to explain here before, we can think of the, sorry, going too far. We can think of the optimal action value function as, given that we chose action A, we consider the probability of transitioning to different states, and then we get the reward at the state we fall, and we consider the discounted value of the best action we can take for each particular future state. So we keep choosing the best actions over the states, and this would give us the largest, the optimal value for the state, for the action value function. But we can consider that to be, if we are improving the policy, we can use the state value function here, because ideally, if our policy gets better and better, then the action that is chosen there will be increasingly likely to be the best possible action. So we can update our Q function by considering the expected future return using the state value function here. And then we can adjust the policy by adjusting the choice of action in state S according to which one maximizes the expected return. So basically we can compute the action value function from the state value function, and then we can use the action value function to choose the best action for each state, and that way inform the policy that we need to choose that action instead of some other action that we are choosing. So using that idea of picking the advantage, the action with the greatest advantage. So let's see how we can iterate in one step for iteration to improve our policy. We have the state value function and the MDP for this. So we're going to compute the action value function, the Q function, from this one. We're going to start at zeros, and now for each state that we have, we're going to consider all possible actions, and we're going to put in our table for this state and this action, we're going to write in what we expect to get in the return. So we have the reward for that particular state and the discounted return that we expect from the next state, and this we can get from the value function. So this allows us to compute the action value function from the state value function that we have. And now, once we have the action value function, we know the expected return for each action at each state, and we can create a policy that simply chooses the action with the maximum return for each state. So our policy now will be, according to this particular action value function, our policy will be for each state the action that maximizes this Q value. Okay, so this gives us a new policy, and now we can do this iteratively, because since now we have a new policy, we can compute a new state value function. Remember that the expected return for each state is dependent on the policy that we're following. So what we can do, the way we can do that iteratively is, for example, we can start with a random policy. We just create a policy that for each state chooses a random action. And now we're going to use the policy evaluation function that we created here, that will converge to the action, to the state value function for this particular policy. So now we can compute the expected discounted return for each state if we follow this policy pi. And now that we have the state value function, we can compute the action value function from the state value function and get a new policy that maximizes the expected return. That is, chooses for each state the action that gives us the best estimated return. And now we do this repeatedly until our new policy is exactly the same as the old policy. So if there is no change in policy, we stop and we have the optimal policy. So this is a comparison, the greedy policy that we have, the safe policy that we propose next that was better, and the optimal one. So we can compare the two. This was the safe policy that tried to avoid the holes, but actually it could be improved by changing, instead of trying to go north here, trying to go in the direction of this hole. This seems a bit strange, but when you think about it, if you try to go north here, there is a 2/3 probability of falling into a hole. If you try to go straight towards a hole, there is a 2/3 probability that you will not fall into a hole, and only 1/3 probability of falling into a hole. And so we, with these changes and the same things here, going down instead of right to avoid going back there to the holes and so on, and we get an improvement in the policy, and this is an improvement in the state value function. You can see the values are slightly higher than the previous one. Okay, so to sum up this part, we saw the idea of reinforcement learning. Our agent is acting and observing the states and the rewards, and this notion of the Markov decision process, which is a process where our decisions for the next step depend only on the current step. So we need to represent the state, observe the state in a way that we do not need to keep track of previous information, so that we respect this Markov property. Then we saw these Bellman equations, which decompose the expected returns into the reward we're going to get on the next step, and then the discounted returns from that state onwards. And this helps us then evaluate policies using those convergence properties that we saw to evaluate the value, the expected return at each state according to that policy. This is the state value function, the V function. And then we can use that one to compute the action value function, the Q function, that will tell us what is the expected return for each action at each state. And this allows us to improve policies, because once we have the Q function for a particular policy, we can see where there would be an advantage in changing the action to a better one at each particular state, and we can do that iteratively. So if you want to read this in more detail, I recommend this book. I covered here in a very quick manner the subjects from chapters 1 to 3, but you have this in more detail. There are some typos in the equations, but I'm going to fix them, and I will update the slides after the lecture. Okay, so let's take a short break and we continue at 5 minutes after 10 with the second part. See you soon.